That's good stage managing. Hit the record button and immediately just stop and take a drink of coffee. Today, we want to combine some of the things that we looked at last week. Last week, we looked at vector fields and parameterized curves, and we want to combine those two things. Those two things are going to combine into a line integral. So a parameterized curve plus a vector field is equal to a line integral. That's how we get a line integral. This is going to be the first thing that we talk about in vector calculus. We are now in the fourth phase of calculus. We have differential and integral calculus. We have sequence of series, power series. We have multivariable calculus. And now that we've got all that under our belt and we're 100% experts on all those things, close enough, and we can get into the fourth phase of calculus, which is vector calculus. So let's talk about what a line integral is going to represent. All right. So we're going to grab a vector field from last week, our favorite vector field, a nice simple vector field. And remember the two things that we care about when we're looking at a vector field. We're going to be interested in two things. All of a sudden, my arrows didn't look balanced. A little better. We care about two things when we're looking at a vector field. Two things to think about with a vector field. There are a few things that we want to think about in a vector field. Number one, what is the flow of the vector field? What paths does the vector field create? What are paths created purely by the vector field? If we use the vector field as direction vectors, what kind of paths will create? So the flow of the vector field, we're going to think using the vector field as direction vectors. The vector field is direction vectors. What kind of paths do we create? Well, we're not the vector field. What kind of paths does the vector field create? So we've seen examples of a vector field that had an exponential flow. We saw an example with a parabolic flow, and we had this example which had linear flow. We didn't do the analysis on this, but the reason I picked this one for the example today, first of all, it's Monday. Second of all, I haven't had a lot of coffee. And third of all, this one is going to be the easiest to find the flow on because we could see what it's going to be. Let's remind ourselves of how that worked. We looked at the components of the ij vector and say this is how the I component is how x is changing. So we're treating this as the dx dt. We're saying dx dt is just a constant 2. Then the j component is how y is changing. So this is just describing the direction of y. So that's just dy dt is equal to 1. Then if we combine these into a dy dx to see what kind of curve we're looking at in the xy plane, we can see that dy dx will just be dy dt divided by dx dt. The dt cancels, so we've canceled out the parameter in this case. Dy dt is 1. Dx dt is 2. And so the dy dx for any flow line is just going to be a 1/2. We get a constant rate of change dy dx, and that means we're getting lines, just like the vector field suggests. It looks like we're getting lines with a slope of 1/2. So the flow here is lines with a slope of 1/2. If I start off at 0, 0, and just follow the path of the vector field says go in this direction, 2i plus 1j, and do that forever. So we do 2i plus 1j, and that's still the direction we should follow, 2i plus 1j. And wherever we start, we get the same. Follow 2i plus 1j, that's your direction. 2i plus 1j, that's your direction. We had to do a little bit of calculation to figure out what the slope is going to be. But the flow, we are getting flow that is lines with a slope of 1/2. That's one of the things that we want to think about when we're looking at a vector field. What is the flow of the vector field? If we just dropped a leaf onto this vector field, what path would the leaf take? This is just a vector field, take the wheel. There's another thing that we want to think about when we look at a vector field, when we're when we're thinking about a vector field. The other thing we want to think about in a vector field is what is it going to be like cutting some other path through the vector field? What happens when we follow some other path through the vector field? Is the vector field pushing us along that path? Is the vector field hindering the path? Is the vector field pushing with or pushing against? Does the vector field push with the path, or does the vector field push against the path? And then by how much? We have lots of directions. We've got vectors going in all kinds of directions. So it's going to be a little bit of both. In the x direction, maybe it's pushing with, while in the y direction, it's pushing against. So that raises the question, how much is it helping or hurting? So the other part of this question is, how much is it helping or hurting? How much is the vector field with or against our path? And in what directions is the vector field with or against the path? How can we quantify this? How can we calculate this? Because that's what we need to do in math class, quantify and calculate. So how do we quantify this and how do we calculate this? Any questions? I think generally I take too much time and build this too carefully, but I want to make sure that we're all on the same page, because it's really easy to just show you how this calculation works, have you practice the calculation a bunch of times, and not really know what the heck you're calculating. I worry about this because the whole reason that this particular calculus book, the Hughes Howlett calculus book, exists is a reaction to that happening. Previous calculus books were like, oh, here's how you find derivatives. And students are like, oh, what the hell is a derivative? It's like, well, shut up, calculate more derivatives. In problems 1 through 1,000, find the derivative. And then we all sat around and wondered why the students didn't know what we were talking about when we talked about rates of change. So we all decided, it's like, well, hey, maybe we should tell them what we want to know about this. I'm just kidding. Secretly, we did, but we didn't tell you enough. Because we told you what we wanted you to know. And then we said, in problems 1 through 1,000, find the derivative. So our words said, here's what you need to know. Our actions said, this is what you need to know. Do you know what I mean? This is exactly the reason that parents of young children are like, oh, why can't you just teach it like you taught me? Well, mom, that can't help her kid with math homework. We did. We just emphasized the wrong things. So I apologize, we've done you harm, but since you're being a dick about it, we're not going to be nice. At least I'm not. That's why I have to be at this school where I don't have to talk to your parents, as opposed to some other school where I would have to talk to your parents. So too many teachers be like, oh, why don't the students know this? And it has the same energy as boomers complaining that kids can't read the cursive anymore. Kids can't drive a manual transmission anymore. I mean, honestly, no one needs to know how to drive a manual transmission anymore. Anyway. So that's why I'm taking so long to build up to line integrals. And I'm trying not to distract you with, in problems 1 through 1,000, do the thing. We want to think about the vector field as being kind of our baseline conditions. There's this flow of the vector field. There's this vector field that's telling us what direction things are going at any point in the plane. That's going to define a few things: flow. And the second thing we want to think about is what's going to happen if we try to follow some other path through that vector field. Sometimes if we're walking along a path in the vector field is helping, and sometimes it's going to be hurting. Imagine if our path through the vector field started at the origin and went in a line with a slope of 1, 1. The vector field is pushing us along. Our path is pushing us along. We've got a tailwind. We're going to be going much faster. If we think about, we're going to be doing less work to get the same thing. The canonical example when we're talking about line integrals is that work is equal to force times distance. We've had to upgrade that because now force is a vector and distance is going to be a vector. And we're not just going to be able to say times anymore. We're going to have to upgrade to a vector multiplication. So in a line integral, we're going to be looking at this interaction between the path and the vector field. And we're going to be multiplying those things. And those things are vectors. And the question is, how much of one vector is going in the direction of the other vector? So we can see that line integrals are going to be our first integral with dot product for the multiplication. A line integral is an integral that will use the dot product for the multiplication. Remember that integration is multiplication in which one of the factors is continuously variable. Dot product is a kind of multiplication for vectors. It tells us how much of one vector is going in the direction of the other vector. That's a gross oversimplification. It gives us a component of one vector in the direction of another vector. This example is an example where multiplication will do the trick. If we follow along the flow of the vector field. It's also going to be very useful because our vector field is constant. If we follow a path, take a path that is also constant, then all we have to do is multiply. But if we trade out one of our factors, if we upgrade one of our factors from constant to continuously variable, then we have to get into integration. That's all we're doing. It's still integration like we always think about it. Just now our multiplication is dot product because our factors are vectors. So the question was, this topic is sort of like what we've been working towards in Calc 3. Yeah. Everything in math, we always get use out of everything that we've done so far. Every time you cover something in math, there's always some kind of use for it. But the other thing that's going on is we're building to the next thing. There's stuff that's useful all the way up, but it's also always building to the next thing. This is why math is so much fun, because there's stuff you can be doing with this at the moment, and you're still building up to the next thing. There's never a time when we're just like, oh, this is just purely just the next thing. Sometimes it feels that way. And so we come up with examples that are super contrived, like a farmer is building a fence along a river. Like, oh, no farmer is going to put 3 sides of fence and have the 4th side be a fucking river. That's a sure way to get that pen flooded and whatever's stuck in the pen killed. I mean, it's just a dumb problem. It's super contrived. Especially when you might want to build a pen up against like a barn. But I digress. Sometimes we have some super contrived problems to help us work through our mechanics that we're working on. But there's always something useful going on, and we're always building to something else. Let's just imagine some paths. Let's just imagine some paths. Let's say one path, and we're going to imagine some paths running through this vector field F. Let's imagine some paths. We're going to imagine some paths in vector field F, 2i plus 1j. Nice constant vector field. Always start with something simple. Let's start with the easiest path. Let's start with a path that just goes with the flow. Path C1. We usually give our curves. We usually name our paths curves. And so we use C and we use a capital C. So C1 is going to be matching the flow, a line through the point 0.01 with a slope of 1/2. So it's going to look like a flow line. C1 goes with the flow. So here's the 0.01, and we're just going to follow this path. So this is the path C1. I want to give the path a direction. I forgot I wanted to give the path a direction. So let's go from 0,1 to whatever next integer point is. So I guess x is 2, y is add 2, add 1. So there's path C1 going with the flow in the vector field. In this case, just a qualitative assessment says that the vector field is definitely just pushing along C1. C1 is a flow line of the vector field. So the vector field is all help in this case. The vector field F is all help along the path C1. The vector field is all push along C1. We're trying to walk this line with a slope of 1/2, and the vector field is just 100% pure tailwind. If we look at the dot product of our direction vector, so the direction vector for the curve I'm adding details that I never stated in the beginning, but let's just have this path go on forever. So we can parameterize this as some starting point. We're starting at the point 0, 1, and we are going in the direction of 2i plus 1j. That's what's going to happen in this curve. I might say this is r of t is 0 plus 2ti plus 1 plus 1tj. If we think about what direction this path is taking, so our direction we're not surprised by this at all because we knew I was picking a flow line for the vector field. Let's just take the flow line, the vector field, and multiply it by the direction that the path is taking. They're vectors, so I'll multiply with the dot product. Two times 2 is 4, plus 1 times 1 is 5, so 5. What's this particular dot product mean? We'll worry about that later. Trying to get the idea. We're going to be calculating some dot products because we're going to be multiplying some vectors, because we're going to be integrating, and this is the multiplication that we're going to be using. So in this case, the vector field was all push. Let's look at a different path through this vector field. Let's say path C2 C2 is going to be a path, is going to be a line containing the point 0, 2, and 2, 0. So we're going to have a slope of 1. So we're going at a steeper slope than the vector field. We're still generally going in the same direction as the vector field, up and to the right, because we've still got a positive slope. We're going up and to the right. But we're not going in exactly the same direction. We're going roughly the same direction, but not exactly the same direction. So let's go and draw that on our vector field. So at the point 0, -2, and we're going in the slope of 1. So this path is going in the same direction, but it's not exactly the same direction. Still going up and to the right, but not in the same amount. So the vector field is pushing we can think of the vector field as still being all pushed, but it's at an angle now. There's no point, in both the x direction and the y direction, we're pushing along, but we are at an angle. So when I say it's all pushed, that means in the x direction and the y direction. Vector field agrees with the direction of the x in the x direction and agrees in the y direction. But the vectors themselves are at an angle. One's at a slope of a half, the other one's at a slope of a 1. So there's a 15-degree difference in the two directions, but generally go in the same way. What we want to see is the what we want to think about is the interaction between the vector field and the path that we're defining through the vector field. Let's make another one. C3, you can probably guess, is going to agree in one and disagree in the other. So let's go through the point 0, 3, 0, 2. And let's go at a slope of -1. Oh, it's going to cut right through this area. Oh, well, it's fine. It's fine. Plan better next time. So C3 will go through 0, 2 and have a slope of -1. So C3 is going to be a line through 0, 2 with a slope of -1. We can see that in this case, the vector field is pushing with the path in the x direction, but against the path in the y direction. If we imagine C3 going this direction. So the vector field pushes with the path in the x direction because we're moving from left to right, but against the path in the y direction, because in the y direction, the vector field is pushing up with 1j, and the vector field is, the path is pushing down with 1j. So the vector field is pushing in the x direction. But pushes against in the y direction. I forgot push is directional. Yikes. The vector field pushes with in the x direction and pushes against in the y direction. The vector field is up and to the right. The path is down and to the right. Both say to the right, they agree in the x direction, but vector field says up, path says down. That raises the question, which one kind of wins? Which one kind of wins in this case? Is the pushing with, is that tailwind in the x direction enough to overcome the headwind in the y direction? Which one creates, is that is the pushing helping more than the pushing against hurting? That raises a question, which one is greater? Push in the x direction more than the push in the y direction. We might look at it and say, well, the vector field is 2j plus 1i, and the direction of the path is 1i minus 1j. So it looks like they cancel out exactly. But another path, what if the path is, we're just going faster, and the path is better described as 2i minus 2j. Now that's going more. That's a lot to think about. More importantly, how are we going to measure how the vectors interact? Remember, the mechanism here is how much are these vectors interacting? To analyze that, we're going to need the dot product. Let's make a fourth path. And then leave you with a cliffhanger. It's like 8:59. A fourth path, I'm going to have go all the other directions. It's going to fight against the vector field. I'm not going to do anything fancy. I'm just going to take this C3 path and send it the other direction. not the other direction this way. So I'm going to start off at 0, 0, 2, and we're going to go down with a slope of -1. So think of the path C4. Notice that the path C4 is being pushed against by the vector field because it's going to the left, and it's pushing against the vector field because it's going down. It's not the exact opposite of the vector field, but it is opposing the vector field. The vector field is pushing against this path. So in the C2 is a line containing, I didn't put a vector field, vector equation in a vector product in there, but we're still going to want to be taking F dot R. So we would need to parameterize C2. On the first page, I had parameterized C1 and written down its parameterization as a vector function and its derivative. Oops. There we go. Wow, this really kind of changes things. Shoot, dt, and then that's just going to be dt. So think about what's going to happen with the C4. C4 is going against. Make some parameterizations, make some dot products, get used to what's going on here is that we're looking at the interaction between two vectors. One vector from the vector field at a point, one vector from the path at a point. In this example, all the vector field vectors and the direction vectors were all constants because everything was just lines. Where are we going to go from here? Since we're like overtime, I'm just going to tell you this is going to be the cliffhanger. Think about what happens if stuff stops being constant and starts being continuously variable. That's where integration steps in. Right now, we're just doing dot product because everything is just vectors. It's the same vector everywhere. But that's not the calculus way. The calculus way is to have shit that is continuously variable. That's why we need to get to integration. Because integration is multiplication when one of the factors is variable. Integration is multiplication when one of the factors is variable. This is what it looks like when you're falling asleep in class. It gets a little blurry and you're like leaning close to the paper and trying like. What? Where'd everybody go? That's because I dismissed class and everybody snuck out super fast. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing. Oh, also, before we go, let me actually stop recording.